Hello, this is Dr. Joe Trout from the Physics program at Stockton University. And today we're going to talk about Chapter 8, Time Series Analysis using Exponential Smoothing. But before we do that, let's take a moment and recap and review what we've learned so far. So what is a time series analysis? It's a time series is a sequence of observations recorded over time. And some examples are stock prices and weather data and sales trends. And our goal is to identify patterns for predicting and for forecasting and understanding the behavior of the variable over time. So the components of the time series we said were trend. This was a long-term increase or decrease. Seasonality, which is irregular periodic variations. Cyclic patterns, which are irregular fluctuations. And noise or residual, which is random variations. So the idea is we take our data, and if all these things are additive, we'd subtract off the trend, and then we'd subtract off the seasonal data, and then we'd subtract off the cyclic data, and what we'd be left with is the residual or the noise. And this should be random because if there was any information in it that was non-random, then we would extract it and use it to help make our predictions. But we're assuming that we've taken out all of the patterns and we're left with just random variation. So in Chapter 7, we introduced the linear model, and the linear model looks like the equation of a line. So with the equation of a line, we had y equals mx plus b, where b was the y-intercept and m was the slope. And in this case, we have our predicted variable or value is going to be equal to b naught, which is our y-intercept, plus b1, which is our slope, times, or the coefficient to our independent variable, and plus some residual epsilon. So this epsilon, you can see, is actually the distance to the actual data point from the line that we decided was the best fit to this data. So what is multiple linear regression? This is a statistical method that's used to model relationships between one dependent variable and two or more independent variables. So it has the form of y equals b naught, some constant, plus some multiplier, so beta 1 times x1, and beta 2 times x2, and beta 3 times x3. And it helps us predict outcomes and understands the influence of multiple factors. So for example, you might be predicting your sales based on advertising spending and price and competitor activity. And you would have time series for each one of these, and you would use these time series to help predict what your target variable is. So as an example, let's use some fictitious data that I made up, and we have 4 predictor variables, and maybe we can consider this to be house prices, which might be influenced by average income of the selling area and gross domestic product, and the unemployment rate and the mortgage interest rate. So here we see our data and also our prediction, and the idea is that we're going to figure out how much each one of these predictor variables helped predict this signal or this time series. So how do we tell if a model is a good fit? Well, if we used just the R-squared value, what you're finding is that if it's equal to 1, that means that all of the points, all of your data points, lie on the line that you have drawn and decided was the best fit to the data. And as it gets further and further away from 1, so r squared goes between 0 and 1, what you find out is that the further you go away, it becomes closer to 0. The formula, but the adjusted r squared value is a modified version of r squared, and it accounts for the number of predictors. So the more predictors you add in, it's almost assuredly going to lead to a better model fit. But the question is that do these predictors really affect the outcome of the model, and how important are they? So the formula for the adjusted r squared is 1 minus 1 subtracted, r squared subtracted from 1 times the number of points minus 1 over the number of points minus the number of predictors minus 1. And most of your libraries will figure this out for you, so you don't have to figure it out by hand or anything. And why you use the adjusted r squared? So it prevents overfitting and decreases when there are added irrelevant predictors. So the key point here is that the higher adjusted r squared equals better model fit after correcting for complexity. So we always try to make things fit as well as possible, but with the least amount of complexity. So last chapter we talked about AIC, and we said it's a measure of quality, balancing fit, and complexity. So the formula was AIC equals 2k minus 2 times the natural log of L. And the interpretation was that the lower AIC, the better model, and it penalizes parameters to discourage overfitting. The use case is that for model selection, so we chose the model with the lowest AIC. And the key points, the key point is that the AIC helps find the simplest model that best explains the data. We also have the corrected AIC, and this is a corrected version of AIC for small sample sizes. So this formula is equal to the actual AIC number plus 2k times k plus 1 divided by n minus k minus 1. And why do we use this corrected AIC? AIC underpenalizes complexity when n is small. So this corrected AIC gives you a more accurate selection. And the interpretation is that the lower the AIC, then the better the model selection when we use it with n divided by k is less than 40. So we preferred over AIC when the sample size is small and relative to the number of parameters. Also have the Bayesian information criterion, or BIC, and this is also a criterion for model selection based on Bayesian probability, and it penalizes for complexity more strongly than AIC. So in this case it's equal to k times the natural log of n minus 2 times L, and the interpretation is the lower BIC, the better model, and it favors simpler models as n increases. So if we look at AIC versus BIC, the AIC penalizes lightly and is good for prediction, and the BIC penalizes heavily and is good for true model recovery. So use BIC when you're aiming for a true model with fewer parameters. We also have the cross-validation RMSE, the coefficient of variation of RMSE, and this is a normalized error matrix as a percentage of the mean of the observed values. So this interpretation is the low CV RMSE, the better predictive accuracy. So typical thresholds like error modeling, energy modeling, the monthly model is less than 15% and the hour model is less than 30%. So the cool key points is that it gives a scale independent view of the model error. Glance is a library that we can use as in R, and Glance is a part of Broom, or Glance is a procedure we can use in R, and it's part of the Broom package in R, and it summarizes model objectives into a single row data form. So it's useful for extracting model level statistics like R squared, AIC, and BIC. And it's commonly used in a pipeline for reporting or model comparison. And it works well with LM and GLM and many other model types. So the library is Broom, and we could use the model, and if we use the LM model and MPG with WT plus HP, and the data is equal to MT cars, and then then you can just run glance model, and it returns R squared, adjusted R squared, AIC, BIC, P values, and some other things. So when to use glance is when you want a quick summary of model matrix, and it's comparing multiple models side by sides and integrating model output into tidy data workflows, and exporting results for reporting or visualization. And glance simplifies post-model analysis. Excuse me. So here's the idea. We'll take our 4 predictors in this time, and we'll just look at each predictor individually and see how well that can predict our data or model our data. And then we'll try combinations such as predictor 1 and predictor 2, and predictor 1 and predictor 3, predictor 1 and predictor 4, and 2 and 3, and 2 and 4, and 3 and 4. Then we'll try triplets, and then we'll try all of them. So if you remember, we want the adjusted R squared to be high, and for all of the single ones, the adjusted R squared is not very good. It looks like P1 is the best, and that's fine. Okay, so then if we look at the pairs, what we find is that anything paired with P1 also has a high value, which isn't surprising because P1 did really well already, so it should be okay. And if we start pairing the 3 together, it looks like P1, P2, and P3 give us a pretty good adjusted R squared value. If you remember, for the other ones, we're looking for the smaller values. So for AIC, what we see is that if we use all of them, we get an AIC of 511. And if we use P1, P2, and P3, we end up with an AIC of about 509. If we look at AIC corrected, what we find is that all of them, once again, does pretty well. But we notice that 3 of them actually does better. right? So what we're seeing is that maybe P4, predictor 4, isn't so important, and that it's actually hurting the model, or at least it's making it more complex. If we look at BIC, right, what we see is that P1, P2, and P3 triplet has the best value, which is the lowest value, and that all of them actually goes up a little higher because, once again, it appears that P4 isn't doing much, and adding it in just adds complexity, right? So we can use these to check out the models. So here's a couple of examples. Here's P1, which doesn't do horribly by itself, and P2 seems to have the trend down pretty well, and P3 doesn't do too badly. P4 kind of looks like the naive method, right? That it's found the value, or maybe the average method, but it's not doing very well. So the top one is P1 and P2, predictor 1 and predictor 2, followed by predictor 1 and predictive 3, and predictive 1 and predictive 4. And once again, all three of these, coupled with P1, seem to do pretty well. P2 and P3 also seem to do pretty well. And if we look at P2 and P4 and P3 and P4, they seem to do the least, right? They don't do very well. If we look at the three of them together, right, we see that P1 and P2 and P3, I mean, just by eyeballing it, looks like it's doing the best job here. And if we look at the forecast at all of them, it also does very well. So once again, if we look at our values, P1 seem to do okay, right? P1 and P2 also do very well, right? And we see that P1, P2, and P3 to match using those three predictors, we get pretty good values, and AIC and a corrected AIC and a BIC all have the lowest values. And of course, using all of them, we definitely get a good adjusted R-squared value, right? That's kind of getting close to 1. But we see that AIC is actually a little higher, and the corrected AIC is also a little higher than just using the three predictors, P1, P2, and P3. This just shows a blow up of the actual predictors and how well they're doing. So P1 seems to not do horribly, and then P1, P2 also does pretty well. P1, P2, P3, although it's a little low on that second peak, it seems to do pretty well. And finally, all of them gets really close. So just to give you the code on how to look at this, right? We can go ahead and load these libraries. And I was running this on a Linux machine, which doesn't have a really good working tidyverse. So I was trying to keep away from that package or library. And we'll go ahead and load the data, right? And get the date from the file, and then we'll train it. The test data. We'll take the data and use 90% of it as a train to train it. So in this case, there's 100 points. So I used 1 through 90, and then the test data was 91 through 100. Then I went ahead and set up our predictor sets. So P1 through P4 by themselves, and then in pairs, and then in triplets, and then all 4 of them. So then in this case, went ahead and computed CVRMS, right? So, and then we went ahead and stored the models, and then we looped over the models for the different predictor sets. And then we used Glance to compare all the model simulations and wrote out the results, and also viewed the plots and the results. Then we made up the plots. Sorry, that was just to view the output. And then we made up the plots, and you can look through this at your leisure. And in essence, it just plotted the plots that we were talking about. So now let's talk about Chapter 8. So we're going to talk about exponential smoothing. And this is a simple yet powerful forecasting tool, and it applies weighted averages to the past observations. And the weights decrease exponentially with age. So the key reason for using this is that this method applies exponential decreasing weights to past observations. So in essence, the formula equals our predicted variable will be alpha times y of t plus alpha 1 minus alpha y of t minus 1. So this is the previous version, previous time step, and then 1 time step back, and then 2 time steps back. And for 2 time steps back, it's alpha 1 minus alpha squared, and we keep working. So each older observation is weighted by a factor of 1 minus alpha to the k. So the implications are that the recent data is more influential, and that older data still contributes, but it has a smaller weight. So where does this come from? Let's look at the naive method, right? In this case, what we said is that any future data will just be equal to the last data observed. So we get the last data observed, and the next data point will be equal. So if the last data observed is 5, then the next data point will be 5, and the next one will be 5, and the next one will be 5. If we look at the average method, what we do is take the average of all the data set, or all the time series, and then it remains the value. So if the average of all of the data that we have is 10, then our next predicted value will be 10. And the next predicted value will be 10, and the next predicted value will be 10. So how about if we do something between this? So we want to still keep the importance of the last data, but we don't want to lose the influence of all the other data. So what we're going to do is, for our next data point, it'll be equal to some constant alpha times t, and plus 1 minus alpha times the previous data set. So in general, what we're going to get is our predicted value, t plus 1, is going to be a function of our last value at t, and then 1 minus alpha, and our last value predicted at t. And t is going to go from 1 to 3 up to t data points. So for example, if we look for the next data point, it's going to be equal to, or the data point at t equals 2, it's equal to alpha y of 1 plus 1 minus alpha, and then the predicted value from 1, 0. And if we look for 3, we get the value at 3 is equal to alpha, the value at 2, plus 1 minus alpha, and the predicted value from 2, and so forth and so on. So what we end up with is yt plus 1 and evaluated from t is going to be equal to alpha t, 1 minus alpha, and the predicted value at t plus 1. So for example, if we look at y at 2 and we have a value for it, and let's just call the initial value y at 0 equal to L naught. So if we look at 3, we said it's equal to 2 plus 1 minus alpha times the predicted value for 2. But the predicted value for 2 is just alpha 1 plus 1 minus alpha L0 or L naught. So in that case, we'll plug in for this value. So when we plug in for it, what we end up with is 1 times alpha y1 plus 1 minus alpha L naught minus alpha squared y1 times 1 minus alpha. So we'll end up with our next value is going to be alpha y2, alpha times 1 minus alpha plus 1 minus alpha squared. And then if we go down to the next value, we'll plug in at 4, we'll plug in for 3. And what we end up with is alpha y3, alpha 1 minus alpha y2, plus alpha 1 minus alpha squared, plus, sorry, there should be another alpha in here, 1 minus alpha to the third times our original value. So when we look at the final, if we look at and make this and find an equation for it, what we find that our predicted value at t plus 1 is equal to the sum of 0 to t minus 1, alpha 1 minus alpha to the j, and y t minus j, and 1 minus alpha t and L naught. So there's several types of exponential smoothing. There's the simple exponential smoothing, or SES, or Holt's linear trend method, or Holt's Winters seasonal method. So for example, with time series with no clear trend or seasonality, then we can just say we could just use the simple exponential smoothing. And what we'll use is alpha, and alpha is the smoothing factor, and it's somewhere between 0 and 1. And what you do is look for the best value. Now luckily we can have the computer figure out what the best value is for us. So how does SES work? We look at the recent observations, and they're weighted more heavily than previous observations or observations from a long time ago. We use a smoothing factor controls the responsiveness to the changes, and a low alpha, the smoother the forecast, and a high alpha means that it's going to be more responsive to the changes. So once again, what we had was the naive method. That just means whatever the last value is, we're going to use it as the next value. Or we could look for the average, and we figure out what the average is for our whole time series, and then that becomes our predicted value. So now we'll start to use this exponential weighting. And for instance, if we look at alpha equals 0.2, then our first term will be 0.2, and our second term will be 0.2 1 minus 0.2, which is 0.8, and we'll end up with 1/16. And then we get 1 minus 0.2, which gives us 0.8 squared times 0.2, and so forth and so on. And if we use alpha equals 4, we get these are the weights that as we go back in time, right? So notice that these weights are getting smaller as we go on. So here it is in graph form. If we start out with 1, right, alpha equals 1, then all of these terms become 0. And we're left with the naive method. And if we go with 0.8, then what happens is the last value is pretty important, and it falls off quickly. The lower the value means that we're going to have more equal weight for the previous sample or observations. So for example, if we have these observations and we're going to predict what the value will be on the 24th, what we'll use is these are to train the data. And if we use alpha equals 0.2 or 0.4 or 0.6 or 0.8, we'll get these values. And the actual value was 2147. So we can see the percent difference between these. So this weighted average, we see what the form is. And if we have, if we use only the most recent value, right, then we end up with the naive value again. We can also look at this in component form. So for simple exponential smoothing, the only component included is the level LT. So we can forecast the equation and it comes out to be equal to L3 LT, and this smoothing equation LT equals alpha t plus 1 minus alpha and the level at t minus 1. If we set h equal to 1, this gives the fittest value, and setting t equals to t gives the true forecast beyond the training data. So if we look at flat forecasts, we have a simple exponential smoothing has a flat forecast function if we set our next value equal to LT. And that is, for all the forecasts, they're going to take the same value equal to the last level component. And remember, these forecasts will only be suitable for time series with no trend or no seasonal component. So what happens in SES? Once all the historical data is processed, future forecasts remain constant, and the flat behavior, and this is a flat forecast behavior, so the level becomes the smooth value used repeatedly. So why? This SES assumes that there's no trend or seasonality, and it only models the level of the series. And if that's true, then the implication is that it's best used for data with no clear direction or cycles, and it's inappropriate for trending or seasonal data. So for example, here's some sample data, and here's alpha equals 0 and 0.2 and 0.4 and 0.6 and alpha equals 1. And what we see is that, right, since they're possibly is a cycle and a trend, then these values probably aren't the best models that we can use. In case you want to try this out for yourself, here's some sample code, and once again we're going to load the required libraries and then load the data and then store the forecast and plot the forecasts. So if we look at optimization, if we have alpha selected by ETS, so we're going to use A and N. So in this case, what we're saying is that there's no trend and no seasonality, and so alpha becomes our component that is predicted. And we're saying that the residual or the noise is additive. So we can load our required libraries. Once again, I was using this on Linux, and the R version of Linux, I found that the forecast library in ggplot2 works pretty well. And we'll go ahead and read in the data, and then we'll get the date and convert the time series. So it's going to assume that there's daily time series, and then we'll fit the ETS model using ANN, so no trend and no seasonality. And we're going to use the first 90 points to train the model, and then we'll print out the chosen alpha that's chosen by ETS, and cat will print out the data, and it says alpha selected by ETS, and we'll look at the model parameter for alpha, and that's /n, assuming you know what that is, to print to the next line. Then we're going to forecast for 10 points, right? And we'll look at the data frame and look at the lower and upper for 80 and 95%, and then go ahead and plot the data. Some of the limits of SES are, of course, that it doesn't account for trend or seasonality, and it's best for short-term forecasts of stable series. With the Holtz method, we extend the linear trend method. So it extends SES to include a trend. So in this case, we get alpha, 1 minus alpha, and the level plus the trend. And the trend is going to be equal to beta times the level minus the previous level, and then plus 1 minus t, and the trend at the previous level. And then we can go ahead and forecast it. So L is the level, and T is the trend. And beta is the smoothing factor. So if we look at our predicted value, it's equal to the level plus H times BT. So the level is equal to alpha times Y of T, 1 minus alpha, the level at T minus 1, plus beta T minus 1. B T minus 1. And B is the trend equation, which is beta times the change in the level, plus 1 minus beta BT minus the B at T minus 1. So in this case, using Holtz method, we can go ahead and predict this variable. But what you see, once again, is that once we make a prediction, it remains constant for there. And you notice that there was a trend here, and we end up there. If we use the Holtz method and we use ETS, where we have selected the residual, that's the first day, and the trend is the second A, and then N means no seasonality. And in this case, we'll get this to, we'll show the trend in there, and at least we're predicting the trend very well. In the last one, what we did was not include the trend, so it was A and N, and we got these values. So we load the libraries, we go ahead and load the data, we find the date, we convert the time series, we fit ETS error equals A and trend equals A and season equals N. And then we go ahead and print the model parameters and we forecast for the next 10 points. Then we can create a forecast data test frame and go ahead and plot the data. So in this case, we're forecast of US population, and we're modeling ETS using AAN, and we find out that alpha is 0.9999 and beta is 0.999344, and we find out what our initial level and B were. And we can look at the AIC and the corrected AIC and the BIC. We see that it's about 45 and 56 for BIC. This is the population for Poland, and what we see is that once again we'll use the error and the trend and not the seasonality. And in this case we find out that alpha is 0.999 and beta is about 0.51. And we see the initial condition comes out to, the level comes out to be about 29, and B naught was about at 0.34. And here we end up with AIC is about negative 48, and the corrected is about negative 46, and the BIC is about negative 37. So to get these plots, we loaded the libraries and we prepared the US population time series. So we looked at the USA economy, and we got that from the global economy, which once again is a data set that's saved. And then we have USA economy, and we look for USA, and we find out what the population is, and this is, we're going to divide it by 1,000,000. So 1e to the 6th is the population in millions. So then we'll go ahead and auto plot it, the US economy at population, and y-axis is in millions, and our US population. And then we'll go ahead and fit an ETS model to it. Once again, we're going to use AAN. So A is for the error, and the second A is for the trend, and the third A means no season, right, which is written down there. So then we can print the model parameters. So we'll report on the fit, and then forecast 10 years ahead with an 80 and 85% intervals, and plot the original data and the forecast and the prediction rates. So the Holtz method, the strengths are that it models the linear trends well, and it's more adaptable than SES, and it's still simple and computationally light. The Holtz-Winner method adds in seasonality, so now we get it adds a seasonal components, so it has two variants, additive and multiplicative, and it forecasts using those components. So the additive is suitable when the seasonality is constant in size, and multiplicative when the seasonal variation changes proportionally with the level. So for example, we could have a monthly demand with seasonality, and we initialize with 2 or 3 forecast steps, and we set alpha equal to 0.3 and beta equal to 0.2 and gamma equal to 0.1. So these parameters, alpha, beta, and gamma, are chosen via a grid search or an optimization, and libraries, most of the libraries that we can use will optimize them for you. But that doesn't mean that you might not want to change them, so you can look at the optimized variables and then decide if you want to stick with them or change them slightly due to your your technical experience in that area. So how do we evaluate the models? We can use the mean square error, or the root mean square error, or the mean absolute error, and we can compare it against things like other models such as the naive or the ARIMA models. So use cases of exponential smoothing are inventory and supply chain forecasting, financial time series, and weather and energy load forecasting. So the tools and the libraries you can use are Python stats model and scikit-learn and Profit. And with R we have forecast and smooth. And there's even some integration with Excel and Power BI. So the exponential smoothing is intuitive and effective, and the choose method is based on the data characteristics, and it works well for short to medium term forecasting. So when you use it, when you need a short-term forecast, when the data is regularly spaced, and when you need a fast, low complexity model. And it's best when there's little noise and there's no need for a component interpretability. Sorry, can't talk today. So for example, a good application is retail demand forecasting, so forecasting daily and weekly product sales, and it helps with inventory planning and avoiding stockouts or overstocks, and it works well with stable trends and seasonality. Or a coal center volume, so it can forecast hourly and daily coal volume. So it'll be helpful in staffing optimizations and reducing wait times, and often has trends and seasonability. So another application is energy load forecasting. So predict electricity and gas consumption and shows daily and weekly seasonality and trends. And the Holt Winters is widely used in utilities. When not to use it, so avoid it when data is irregular or missing, or there's structural changes such as pandemics, and there's complex dependencies. In that case, you might want to use ARIMA or Profit or ML models instead. So just to pull everything together, we have a bunch of models, right? And we have this SES model or ETS model, and what we can do is set it up so that we can use either trend or seasonality or noise, and all of these can be either additive or multiplicative. So we can also have multiplicative error models. So in this case, we could have, so we set the trend either to N or to A or to And the seasonal we can either set to A or N, and they can be multiplicative.